Very good. So Margherita will continue from last time.
Thank you very
So
much.
this is being recorded.
Yes.
Yes. Okay, so please still ask questions.
Not stupid ones.
It doesn't matter, there are no stupid questions. Here first let's see a quick summary of what we already saw last time. So I started introducing a Grassmann algebra as the set of all polynomials I can create starting from n abstract generators. And the only requirement is that two generators anti-commute and the square of each chi is equal to 0. And then we construct all the possible polynomials, and we have seen that because the square is 0, then each variable chi can appear to the power 0 or 1 only. So a general element in the Grassmann algebra can be always written as a sum of one real number, a sum of polynomials of order 1 in one variable, so I have just 1 kj, or I have a polynomial of order 2, and the maximal order is n, when I have each variable exactly once. And that's, here I get all the elements in my Grassmann algebra. We have also seen that there is a special subalgebra of G which is made of all the polynomials of even degree. And for an element in this subalgebra, we can always write P as a real number plus something where n is an even element in the Grassmann algebra. It's made only of Grassmann variables, and so it's important. If I take a high enough power, I get 0. And since V0 is a true object, this is the body of my element, and this is the soul. And this is the soul. So I can say that this element is positive if the body is positive. So I have a notion of positivity. Now, using G even, I can generalize any function which is C infinity from R to R to a function going from G even to G even in the following way: f of V, where V is given by this decomposition, is a Taylor expansion around the body. This is a real number. Now, since n is important, this sum is always a finite sum. There is never an infinite sum. Okay, and then with that we define also the integral. Now, using this, then we went to define a supersymmetric version of a statistical mechanics theory, where our field now, so we always work on a finite cube in a lattice. And our field now goes from lambda to R2 bar 2, which means that each the spin at each point has 2 real and 2 Grassmann variables. Now, this time I was more careful compared to last time, so Xi and eta are Grassmann variables, but actually now you're a bit more experienced. If I say this, it will not shock you. X and Y, they are not really real numbers, they are actually even elements in the Grassmann algebra, generated not just by the Xi, but I could even add a few additional Grassmann variables that will be parameters. And I will use them to define later supersymmetries, super transformations. Okay, so now for this vector I can define a scalar product, which is the usual scalar product plus a term that takes care of the Grassmann variables. In particular, if I take the scalar product of phi itself, I get x squared plus y squared plus 2 psi eta, and you see that the body of this even element is x squared plus y squared, and that's positive. So I still have a notion of the norm, but it's just when I take the body. Actually, I should even take the body of this, because this may be an even element. So with this, we can define now an action for this superfield. And now I try to write it, compared to last time, a little bit more generally. So last time I just wrote here phi Laplacian phi. And I can always do integration by parts and write it as a sum of gradients. And now I can make this even more general and take a Laplacian which is inhomogeneous with different weights. So here, instead of having the same weight beta, I can have different weights for each pair. So now my Wij equal Wji is symmetric and it's strictly positive for every pair of nearest neighbor points. And now to make this faster, whenever I have 2 points at distance 1, I will write I tilde j. Okay, so I think that was so using that. So the only difference is last time here I had a beta, and here I had a beta which was the same for all the pairs. Now with this function S, which is now an even element in the Grassmann algebra, I can define exponential of this. This is well defined because it's now a function from G even to G even. So I can define this measure, which is the usual measure, but now we have this super vector. So we have E minus S d phi times normalization. And one of the last things I explained was a very important effect of having both real and Grassmann variables, and that's the localization theorem. So we have seen that all these expressions are invariant if I do linear transformations that leave this superscalar product invariant. In particular, we can do linear transformation that mix the 2 real with the 2 Grassmann variables. And these transformations are responsible for this localization theorem. And the localization theorem states the following: take any function of this field, which is of the form a function only of scalar products for any possible pair. And what I need is that this function is fast decay and regular enough, let's say it's infinity. Then I can do, oh, I forgot the phi here actually. I can do the integral of this function over this space. And I don't need to compute the integral, the result is just the value of the function when I take all the phi equal to 0. Special application, take here f phi equal E minus S of phi. If I look here, I see that indeed this is a function only of scalar products. So I apply my theorem and I see that the integral is just the value of the function when I put here 0. And f of 0, in this case, is E minus S of 0, and that's 1. So that's one beautiful effect of supersymmetry. We never have a normalization constant. And notice that this is true independently of what are the constants I put here, here, or here. Actually, I can even put here H to be J dependence and this G to be J dependence. Okay. So, last time I started a little bit explaining what was actually the main topic of the seminar, which was trying to show you there is a connection between this kind of supersymmetric statistical mechanics and certain stochastic processes. And last time we have seen one example, but I will repeat it. So, sorry. Statistical mechanics and stochastic processes. So these we have already seen last week. Example 1, we take the weakly self-avoiding random walk. I will give you a list of references at the end because otherwise I'm sure I will again late. So how did we define these? We start with a simple random walk in continuous time, which I call xt, on jump probability, so the probability that at time t plus delta t I n in j, knowing that at time t I n in I, and knowing the history up to time t is equal to 0 unless I and j are nearest neighbors. And if they are, the jump rate is wij delta t plus little o. So now the jump rate will depend on the edge. So this process is Markovian. Which means, and I will set W, the corresponding average. W, to remember that we have inhomogeneous jump rates. Wij is Wji. That's and A is the starting point. Now I think I have to do that. So the very last theorem I wrote last time, I think it was the last theorem, I will call it now theorem 1. And it says the following: take any 2 points in our volume lambda, set, let's say that Lj of t is the local time of j, so the total time our process spent at position j until time t. Then we have the following relation. If I take the average in my simple random walk with inhomogeneous jump rates of the event that at time t I n b times e minus h, the total time, times e minus 100 g.
There's a plus missing somewhere.
Sorry?
So it's indicate the function. It's 1 I minus j plus your probability.
Sorry, you want the definition of
No,
this?
further up. in your
Above,
conditional
here?
probability. Even further up.
Inside here?
No,
Sorry. Yes, it's the indicator function that I and j, I tilde j, which means I and j are nearest neighbors.
Oh,
Sorry, yes. I'm lazy, I didn't want to copy all the time I minus j equal 1. For the rest, the notation is okay. Okay, so now we have, and now the last term, there is a g of t squared, so we have a weak repulsion term. We integrate over time between 0 and infinity, and this expression is equal to the 2-point function for the supersymmetric statistical mechanical model. So the integral will be phi lambda e minus s phi. We are integrating over r into lambda, and we are taking the 2-point function. So maybe I was right here where, so well, maybe I see this in words. So what is the advantage of having this? Let me just, so let's look at these. So here we are relating properties of the weakly self-avoiding random walk to a field theory, a phi 4 theory, but the price to pay we have also Fermions. So this is saying that, okay, now we write it here, that the weakly self-avoiding random walk is connected to SUSY phi 4. But that means that if I want to study this process, process, this probability measure, I can study this field theory. And here we can apply renormalization group analysis. So, and here we can do RG analysis. And this is what Roland, David, and Gordon did. And I think you were explaining all this. Yeah, that was what you were explaining in detail the first week. So you have seen this. Good. So now I will give you an example where you cannot do renormalization group analysis, but you still have the symmetry. So my second example is the so-called vertex reinforced jump process. In short, DRGP. This process was introduced pretty recently by Werner in 2000. But the truth is that behind this process, the motivation was another process which has a long history. So there's pretty a long history behind, but I don't have time now to explain all that. So how is it defined? It's again a continuous time process. So we have an ST, t equal to 0, on data. And once again, I want the jump probability. So we take the probability data time t plus delta t and j, knowing at time t I am I, and knowing the history up to time t. So at the beginning it looks the same. I start first characteristic function that I and j are nearest neighbors. I multiply by the weight I and j. So until here is the same, but now comes the difference. In addition, I have the factor 1 plus local time at arrival point at time t plus integral delta t. So here I'm jumping from I to j. So I am reinforcing the jump rate depending on how much time I already spent at the arrival point. So, what are the first main properties of this? So this factor, well, first is creating an attractive interaction in this process. You prefer to jump back, so it's attractive. And second, this L depends on the whole history of the process until time t. So it's no longer Markovian. And to fix the ideas, from now on, I will take any average in this process when it starts at A as average VR. Now, actually, there is not just one, but there are several relations between this process and a supersymmetric statistical mechanics field theory. And I will try to show you two relations. So there are two relations between DRGP and SUSY.
Margherita, what's the A? Is that the starting point or what?
It's the starting point.
Okay.
Well, unfortunately, I had to cancel this, but you have it on your notes. And I still have theorem 1. So you can guess that one relation will be some kind of generalization of this identity. So relation 1 it's an analog of theorem 1. But life is not that simple. I have to change a few things in this formula. So the first thing I have to change, I cannot work with a inhomogeneous simple random walk. I have to work with the joint process, where you don't just look at the evolution, the position of your particle at every time, but you look at the same time at the position of the particle and the local times, how much time it has spent at each particular vertex. So this is the process xt, and here I have L, so how do I call it, Lj of t for all j and data. So this process is evolving on a huge space, but the advantage is that this process is Markovian. And somehow on this side of the equation I need to put a Markovian process. So I will denote by average on E W, but now here I have two starting parameters, the starting point and the starting time. Okay. Now what else do I need? Yes, then I cannot, it's not enough to work on the space R22. We have to use another supersymmetric space. So we have to go from R22 to the space H22. And this is a supersymmetric extension of the hyperbolic plane. Of H2. And we can see it better in a given parametrization. So what did we have here? What was our field here? It was a field with 4 components, 2 real and 2 Grassmann. To construct H22, I take exactly this vector, but I have to add one additional component. So I now have phi tilde, which is now the same. So now to make it clear, I will put the last coordinate at the end. Normally you put the bosonic coordinates all together and the Grassmann coordinates all together, but just to make clear, so I put this additional coordinate here, and psi and eta are Grassmann, and x, y, and z, they are again in G even, so the even elements of the Grassmann algebra generated by all the possible psi and eta, and eventually some additional Grassmann variables that will act as parameters. Now on the space R22 we had a scalar product, and the scalar product was phi prime is x prime plus y prime plus c eta prime minus eta psi prime. And now, what kind of scalar product we have here? Phi tilde prime, I put an h for hyperbolic. Well, it's almost the same. I have x prime plus y prime plus c eta prime minus eta psi prime. But now there is this additional z, and here I change the signature. Is a minus. So if you like Minkowski space, this z is equivalent to time in Minkowski space. Now, if you think about this, you see that actually what I wrote here is just the original scalar product plus the additional term. Okay? Everyone is meeting now. So, what's new about this object? Well, here we have just seen that phi has positive volume. So that was nice, it was like an ordinary norm. But here you see immediately it's not true. Phi tilde h, this is phi minus x squared, and this is impossible. So remember, I think unfortunately I cancelled the action, but if you go back on your notes, how did we construct the action for the field? We had a sum over gradient squares, and then there was a sum of phi j, and so on. And it's very important to guarantee integrability that these objects are positive. So here it's hopeless. So to make things work, we have to add an additional constraint. So we need to add a nonlinear constraint. And the constraint is the following. We require phi tilde h to be equal to minus 1. Why minus 1? Well, if we plug it here, we see that this implies that z squared is equal to 1 plus phi phi. So now z is a function of the other fields. And if this is positive and this is 1, this means that z, well, we have to choose first one particular root, then we set z to be equal to the square root of 1 plus phi phi, and this is certainly larger than equal than 1 in both. Let's see, to check if you are following everything. You may get worried because how do we define the square root of an even element of the Grassmann algebra? I have E0 plus n. Well, I take the Taylor expansion, but the Taylor expansion is ill-defined if I have here 0. So if I cannot expand around here if the body is equal to 0. But here it works because this is something that has positive body, and I have here 1, so there's never a problem. Okay, so now that I did, if you like general relativity, imposing this constraint is telling you that, forgetting the Grassmann part, you are taking time-like vectors. So this is equivalent to say z time and phi tilde you are inside the cone. You can, it's a point you can reach going at a speed less than the speed of light. Okay, so now we have everything. Yes, so finally, so I would be tempted, so maybe you write here in a small corner, you look on your notes, what was the action we had before? We had a sum of gradient phi, and then there was a sum over j, phi j, and then the same phi j square. So I would be tempted to say, well, all I have to do now is to replace this scalar product with the hyperbolic scalar product, my fields by the phi tilde, and that's it. Well, actually it works and doesn't work. This term actually works fine, and even if this scalar product is not positive definite, with the nonlinear constraint, now it is positive. So Now this is perfectly well defined. But now you see that this term is just a constant, because this is like the norm of our vector, and that's -1. So from this term I get nothing, and from this term I get nothing. And now we have one problem. Here, this part of the measure is translation invariant. I always need something to break translation invariance. So I have to get rid of the case of constant field. So we have to add something. And this something cannot be of this form. So the action we need S, as the last ingredient, goes to S tilde of phi tilde, which is, as before, it's a 1/2 sum of the j tilde, j prime, sorry, phi. So this time it's the hyperbolic scalar product, and I'm taking the larger vector. But then I have to add an additional piece, which is h sum over j zj. You see that since we have chosen z to be square root of 1 plus phi times phi, this as body is larger equal than 0. You can think of these as like a magnetic field term. You can always write these is equivalent to take phi j tilde scalar a particular vector, where E is the vector where I have x, y, psi and beta equal to 0 and z equals 1. So we are just multiplying, we are breaking, so we are multiplying by a vector which is in this form, which is the magnetic field. Okay, so now when we have these, at this point we have everything. So now we can define the probability, the measure exactly as before. Here. So now mu phi becomes mu phi tilde, which is as usual S tilde phi tilde. Here I have a v phi tilde, and in principle I should divide by z. But we will see that again z is equal to 1.
So E is just 0, 0, 0, 0, 1.
Yes. So E corresponds to take x equals 0, eta equals 0. But then you see that automatically z must be equal to 1 plus 0 squared, if I want to remain on the same hyperbola. And if I take the scalar product, what I get is actually, okay. If you want to be really precise, I should take minus this, and then the scalar product gives me minus z. Well, then I get here plus z. I have
So now it's no longer true that z lambda is 1.
Sorry?
Z lambda is no longer 1.
Actually, it is still equal to 1. We will see it in a moment. Still by supersymmetry. Okay, let's see. Did I write all I wanted? Yes. So, right. So now you have to keep in mind that now here z is not an independent variable. Z is a function of phi given by this expression. So I should write it here. ask what is the why. So what is the partition function? The partition function is an integral over h to lambda d phi tilde d minus s tilde phi tilde. But since z is not an independent variable, if I go to this parameterization, I can rewrite this as an integral over the flat space as before. I have d phi, it's no longer phi tilde. I have to pay a price, and the price I have a Jacobian which is zj of phi j, and here on top I have s tilde, and now in phi tilde is now a vector phi z of phi. Now let's look a little bit what is this. If I go back there, I can reorganize this as, so there will be a piece which will be phi, the
So
Laplacian
this is just-
phi.
You just sort of define your integral like that.
Basically, yes, you're right. Yeah. That, I agree. You
Unless
define your
somehow
integral like that.
define
I agree.
super manifolds
Well,
or something
you are
you don't want.
inserting a
You can actually do
delta and you integrate, but yeah, basically that's the. I agree.
But it's the same as if you do.
It's the induced measure from the ambient space, if you wanted to do that. It's the induced measure from the measure column in Calcium was doing the Calcium space. Not so easy to like go through and calculate, I guess, but like it's the usual hyperbolic measure.
You have to choose coordinates, and this is one possible coordinate system. Okay, now if I actually take this expression here, you see here I have a piece which is just the original scalar product, and then there will be a last piece where I have a gradient of the z minus z prime square. So actually, what I have here is the old term I had in the original action, and here there will be in addition 1/2 the sum over j tilde j prime, w j j prime. But now, what is z? So here I have something which is invariant under supersymmetric rotations. And z, well, z is a function of the scalar product. So this is also invariant under supersymmetric rotations. So again, this function has the right properties to apply the localization theorem. And I use exactly the same localization theorem I just wrote. So once again, this integral by localization theorem. And you see also this term, the z is a function of a scalar product. So it is invariant under SUSY rotations. So all this is equal to the value of the function, so the product of j, zj of 0, e minus, and here I have j as tilde, computed as 0, and z of 0. Now, what is z of 0? Z of 0 is the square root of 1 is 1. So if I look at what I had here, each gradient will give 0, each gradient here gives 0, and even here, the piece which was like a mass, where I have 1 minus 1, 0. And here I have a product of 1. So this is product of 1 over 1. So once again, the partition function is 1 by the same supersymmetry. Okay, so now finally I can write the representation. Here. So again, I take any 2 points in lambda. take anything lambda. So we take, once again, I take the average, but this time I take the extended process with starting point A and initial time 0. And with non-uniform jumping rate. Again, I take the event at time t, I am v, and I have here an e minus h, the total time. We integrate between 0 and infinity, dt, and now this is the two-point function of this new supersymmetric model. So it's the integral of h to lambda d phi tilde e minus s tilde of phi tilde x a s. Which I can always write in flat coordinates if I choose the representation I gave you as d phi product over j delta j of phi j e minus s tilde of phi z of phi, and then you see. I don't know what, maybe when I don't move, well. Now, I can already remark something. You see, if I naively, I could look at this expression and say this expression is Gaussian. I'm very happy. But then, when I really look at the independent variable, I see that there is a first piece which is Gaussian, but then there is this piece and the z depend in a non-linear way from the phi. So this is far away from any Gaussian. So it's not clear at all how to even start renormalization. I still missing something, yes. So this theorem was proved recently by Roland. Tyler Helmut. And this one. Okay, now I think we need to put another. So this is the first relation, and you see this is almost like the relation between Wilkie set avoiding random walk and phi 4. Except the theory we get is not the local perturbation of a Gaussian. Now I have a little bit time, okay, just have time to just write the relation. So you may want to have directly a relation between the stochastic process xt and not the larger stochastic process, the joint process with the local times, and h22. And this you can do. So this is directly you want to connect h22 directly with xt. And actually the answer, yes, you can do it, but there is a price to pay, as usual, and you have to look at a time-changed version of this process. Actually, we need a and now, why is this? Well, there is a first key remark. Here, the reinforcement is to the power 1. So it's linear reinforcement. The jump rate has linear reinforcement. This implies, and it's only true for linear reinforcement, that this process is a mixture of Markov chains. Actually, of Markov-Jones processes. And this is true only if you first take a time-changed version of this x. So first, we need to do a time change.
Maybe a quick remark. I mean, the formula above, you can also put any function of the local time, so you get the complete
I was
process.
waiting for this. Yes, that's what Tyler told me.
I mean,
But
you
he
have
told
the
me also
complete
that in
process.
principle you may get also at the end the mixing measure, but he did not think it did not. He didn't have all
No,
the
but
details.
you have the complete process at any finite time. That if you put a function of the local time, I mean, it's not.
Yes,
I mean,
still, but I mean to prove transience, we needed this other representation. I mean, there's another representation where it's easier to see. Okay, so first I have to take a time change version, which means I define Tj as 1 plus Lj square minus 1. And the point is that here now we have a relation that allows to computations. Now, it seems a bit strange, and if you need details, this is done in the paper by Untitled. So, you get a new process, which a new jumping rate. So, what is now the, I want this process to have exactly the same properties as my starting process. So, if my starting process escapes at infinity, this also escapes at infinity. If the process comes back, this must also come back. And this time change satisfies that. But the jump rate now seems strange. So if I take, so this is equal to, okay, now, hold on. I have the same as before, I and j must be as neighbors. I have always the jump rate ij. This time I divide by 2 and I have a ratio. Sorry, ij. So this time you have a reinforcement which depends on both local times, at the arrival point and the starting point at the arrival point. Now, so this looks very strange. The nice thing is that now I will denote this by tilde.
Excuse me, can you just repeat how tau and t are related?
Sorry, how?
Tau and t, or how do you define your time
So
changing?
this part is where I really don't know well. So I know that this is the part. So there is a paper by Untitled and they do 2 or 3 time changes. That's really, I'm an analyst, so I do the analysis part. I can tell you what I understand. So they define this time change. So if you have this local time, this is the new local time. It's a random time change, and it's random.
Okay, so it's the time change which makes sure that in the new time, the t's are the new local time, and then you can kind of just
You can write also the inverse function. Okay, so well, actually,
it's something like sum of one of these two. Tau is equal to, you just get this function here, of 1 plus Lj squared minus 1. And it's tau is something like sum over all of those.
yeah, but sort of bit some presumably on sort of bits of increments of when you are on a given side.
It includes the total time depends on all of them. Like if you looked at if you looked at the graph of the 2 times, it would change randomly as it goes along. It's just something like the sum of like this or its inverse over all sides.
so it's not such a strange. It's but each time I have to rework it once again because it's. But okay, just believe me, there is some time change. So what is the main effect of this? Well, the first effect is that this new process is a random walk in a random environment. So I will write the theorem, which is 3. So first important effect, this new process, I take the average of some, well, I guess it is some local observable, This is the same as taking the average of the same object, but this time we take a simple random walk starting at A with some inhomogeneous weights. And these inhomogeneous weights are now random. And now I have to take the average over the randomness. So first I will write something, but then I have to take this away. So this is the law of the random environment. Now, actually, one can be more precise. You want to write explicitly this measure. And you can do it if you use a random field, a scalar field. And now W is going to be a function of this scalar field. And what I have here is a probability measure, not for W, but for U. So now I'm parameterizing the random environment through this random field. And what is the relation between this random field and the jump rate? Is the following. The jump rate between I and J is given by, now each time I have to check because I'm certain going to write this wrong. How? Yes. No, I didn't write it. How? Okay, I remember it. This exponential u at the arrival point is the start point. Okay. And this relation was proved by Sabo and Teres in 2013. They proved much more than that. They proved relation to another stochastic process. But the big surprise at the time was no.
So now this expectation is just a simple random walk. The one on the
This is a
right.
simple random walk.
It's a simple
Exactly.
random walk. And that mu,
And this is a probability measure.
which one?
I have to give it to you. I didn't tell you yet. You
It's
didn't
not
say
the
it.
same-
I
not
didn't
the
say
same
it.
mu
It's
as
connected to
before.
H2. That's the point. Now this is going to be connected to H2. Yes, so there was a question.
Maybe
You
at
want
the
to
end.
get about something?
No, I don't think so. I was just wondering, there's nothing here that prevents you from allowing a walk to jump from where it is and end up at the same place? No, you could do that, right?
Yes.
Yeah. So this is a strange consistency condition on all of these things, because it would, oh, anyway, never mind. Go on.
Well, no, sorry, wait, what do you mean? No, when you do a jump, you have to jump somewhere else, then you can come back.
Oh, so you
No,
can,
sorry, you cannot
would
ju- you
not
cannot
allow
stay
a
at the same
jump
point,
to
no.
the same
Good
place?
job.
No, what you do is that you are at some
Oh,
point,
it's a continuous.
you're fine,
random
so
walk.
what you
It
do is
doesn't
that
make any difference.
you stay there for, actually what you do is that you start running, well, it's, here it's less clear, but in the beginning, take the initial definition. You run, there is an alarm clock, a random alarm clock on each of these.
Yeah, no,
edges.
I understand
Okay,
how
when
that
it rings,
works,
you jump.
right.
But you have to, when you
So
jump, you jump somewhere
I
else.
would, you won't be, allow me to put a little loop in this graph,
No.
so that with a random clock on the loop.
No, I don't
If
think.
you put the
Well, I
loops-
don't know, I never tried. It's a good question.
If you put the loops in, it wouldn't change either the x or the y.
Well, I guess what would happen, you could
This
jump
could be a
here, but sooner
rabbit,
or later you will jump somewhere else.
this could be a rabbit hole, let's not go
Exactly.
down it. But
Okay,
these,
where was I? Now I lost my here. So, right. And now the question is, how do I relate these? I can actually write you the measure. I cannot, no, not right. So, second relation would be, well, this measure u is connected to H2. And actually this was noticed for the first time by Martin Bauer. And what is the exact relation? I try to write it using the minimal possible new notation. So take an integral over our probability measure of some function that depends on exponentially j for all j. It's just for convenience I could put in. Then this is the same as taking our supersymmetric model, take S tilde, phi tilde, and now here what is the observable? Well, it's just this function where I replace exponential u by x plus z. This f of all j. And so actually this measure is a marginal of this measure.
xj plus z.
Xj plus zj. So exponential u equals xj plus zj. And actually there is no mistake here. I can actually
Try to read the argument of the function.
it's x plus z. Well, maybe it will be clear if I do it quickly. 2 minutes, and then we can stop. I will never manage to get to the proof by supersymmetry. Just to convince you that this is logic.
I'm
You
a
just
bit
want change
confused
of coordinates.
about the statement. So what does A say and what does B say?
A says that this time change VRGP is a random walk in a random environment.
Right,
It's
but,
a particular, they gave the exact formula of the mixing.
oh, but you're not gonna tell us what that formula is.
I mean,
Oh,
depends
okay.
if
Okay.
I tell it.
So
Later,
does B sort of.
I can write it down. It's
What the form-
Well, that's what I wondered, whether B was
Sorry?
telling us what mu, is B
No,
telling us
no,
what
no.
mu is? No.
He is telling you the relation. No, he's actually he is telling you the relation between the supersymmetric H22 and this mu.
But one can sort of take B as the definition of mu. It determines the mu.
You can sort of take the.
Well, it determines the mu, but I can take B as the definition of mu.
No, that's not true. This was totally independent. We had, because this model, this H22 model was constructed by Bauer in a completely different context as a model from quantum diffusion. And we studied it in a totally independent way. And at some point, independently, Christophe
so
Sapolsky
you're saying that that's not how you came across the mu, but
Exactly.
after the fact, I can still take that as the definition.
Well,
of mu.
we discovered, well, it's not a definition, we discovered that when you take you change coordinates here, you have to change coordinates and integrate out 2 variables, and after you do that, we were extremely surprised to discover that we ended up with this measure.
I think Martin's saying that you cannot have 2 mu's that will satisfy this equation, that this uniquely determines mu.
No, of course there are not 2 mu's that satisfy this equation.
So then it's a definition.
If you want, but certainly it will not tell you what is the form of mu. If you, I can write it down for you, but sure, of course. You can take it as a definition, sure.
Is there you have no magnetic field now, or do you?
Yes, there is still a magnetic field. I can now, okay, if you are now, what he's complaining about is that the magnetic field is, the magnetic field is like you can, the way, when you take the first representation, interpret it as a Killing grid. But in this representation, you have to interpret it as the true starting point of your process. So actually you have to add this an additional point, and you could put an H, a magnetic field, which is different at each lattice point. You could even put only H at one lattice point, and that will be the starting point of your book. But here I didn't want to make all this, I just wanted to give the idea. So very quickly, what is the idea of getting going here from here to here? You do a change of coordinates, and if you work with hyperbolic manifolds, one standard coordinate system is the holospherical coordinates, and they correspond to send x, y, psi, and theta to u, s, psi bar and psi, where these are two even elements in the Grassmann algebra, these are two Grassmann variables, and the mapping, it's easier to write in the opposite direction, is the hyperbolic sinh of u minus exponential u s squared over 2 plus psi bar psi. Y is s exponential u, and then certainly the right is wrong. Psi is psi exponential u, theta is psi bar exponential. Now, if you take these and you plug in the constraint for z, you find then automatically z must be equal to hyperbolic cosh plus exponential u s squared over 2 plus psi bar s psi, which means that if I take z plus x, these two terms go away and we get exactly exponential. And now you should be no longer surprised to see that I wrote here x plus z and here exponential. There is one last remark. Once I go to these coordinates, if I condition on u, unfortunately I don't know where to write. So if I condition on u, s, psi, and psi bar are Gaussian variables.